Okay, welcome to the first example. In the chapter of bending, the question reads, draw the shear force and bending moment diagrams for the cantilever beam shown in the figure below. Okay, so we start off with givens, and to be honest, there's not much we can write in givens. Actually, nothing comes to mind, so we'll skip it for now. But I mean, there are we're going to be introduced to the bending stress equation, which is that, but we're not going to use it in this example, right? So this example just is just concerned with bending and shear moment diagrams. Or no, shear and bending moment diagrams, yeah? Okay, so we want to find Vx, our shear force diagram, and our bending moment diagram, right? So how do we approach finding this lovely guy or these lovely guys? Well, firstly, we want to find all of our forces that act on our beam. That's number one. That's simple statics, right? So I have a fixed connection here. I'm going to have an N, a V, and an M, right? So I have to find those. The N doesn't concern me at all when we're dealing with these problems. So, and you can even tell, since there's no other external forces in the X direction, N is going to be 0, right? But we'll run through that right now. So first step is always a free body diagram to find all your forces. And it's simple statics at this point, yeah? Okay. We will write this as lovely. Right, this is point A, this will be point B, C, and D. This is 2 meters, 2 meters, 2 meters. What else do we have? Let me zoom this out a bit. We have our external force right here of 19 kilonewtons acting up. We have this distributed load, but I can represent this distributed load as a single load of 6 kilonewtons, right? By multiplying 3 times 2, the distributed load multiplied by the distance, right? And I will put that down. So this is 6 kilonewtons. But for shear and bending moment diagrams, I want to make sure that I do not forget that this is actually a distributed load, right? So I'm just going to draw it in the background just so I make sure that I do not forget that this is actually a distributed load, because that is important. So 3 kilonewtons per meter. But again, for force summation or moment summation, I use one or the other. And in this case, I'm going to use this one, right? And it acts 1 meter in the center, right? 1 meter. Okay. Now I can go on to finding my M and V, right? So I have M. I'll assume it's positive at A. N, right? And A. I know it's 0. I'm just writing it down. And V. So VA, right? And to find them, how do I do that? Again, easy stuff. Just statics at this point. I take a sum of forces in the Y direction. Assume positive up is equal to 0. I'm going to end up getting that my VA, my shear force at A, due to this reaction, due to the fixed support, is equal to negative 13 kilonewtons. And what does that mean? That just means that, again, this is actually acting downwards. But I'm not going to change it on my diagram, right? Doesn't really matter. Okay, how do I find the moment at point A? Well, I do a sum of moments, right? And I can do some moments about point A, set everything equal to 0. And I'm going to end up getting, similarly, it's also going to be negative, which means I just misrepresented the direction. It's going to be negative 8 kilonewton meters, right? So actually it acts clockwise, right? I can also write this as MA is equal to 8 kilonewton meters, and then specify the direction, so clockwise. It doesn't really matter. Okay, beautiful stuff. Amazing. I found all of my all of the forces and basically moments that act on my beam. I can start doing my shear moment diagram. And there's 2 main ways to do it. There's the long way, which is why this is going to be a long video, right? And that's called the equation method, or method of sections. And then there's the easy way, which is absolutely beautiful, but you know, sometimes it'll ask you, like a question will ask you, I want you to do method of sections, right? And you have to do it. So unfortunately, we got to know how to do that. So yeah, let's just make this a bit smaller. So we're going to do equation method or method of sections to find the shear moment diagram firstly, and then at the end I'll quickly show you how to do the quick way. Okay, so equation method for shear moment diagrams. Shear moment diagrams. Okay, so the equation method basically, what does it basically say? It says that I'm going to start at my point where, like, I'm going to basically split my beam into sections where nothing changes with regard to the, and this will make more sense when we actually do it, but like a quick explanation, I'm going to split my beam into sections where nothing changes with regard to the moments, to the external moments and the external shear forces, right? So from A to B, from 0, from one, and if I call this distance x, right, and it starts right here, from, for example, x is from 0 to 2, right? Nothing changes, right? And then when I get to 2, something changes, right? I have this 19 kilonewton force, right? So I have a change, right? And then, okay, I'll do a new section, right? And from this section, I'm going to get an equation, right? I'm going to extract an equation for my, my shear force and my moment, right? As functions of x, right? And I can plot these functions, right? And that's the whole point of shear moment diagram, right? Okay. And then once I have, for example, a section from 0 to 2, I can be like, okay, something's changed. I need a new function, right, to represent my my shear force and my moment throughout this beam. And again, this one might be from 2 to 4, right? It's going to be from x is equal to 2 to 4. It's only these equations, these expressions are only valid in this range, right? And then finally, in this case, I'm going to have one from 4 to 6, right? A new expression, a new equation that represents my moment as a function of my bending moment as a function of my distance throughout the beam, x, and my shear force as a function of x, right? So that's the idea. We'll get to actually doing it, and it'll probably make more sense. Okay, so we can start off with letting x represent a distance on our beam from 0, anywhere from 0, starting at 0, anywhere to 2. It doesn't have to be from 0 to 2. It could, like, we're basically cutting a section, right? Let's say this is section AA, right? But this section can range from, it can go from 0 to, I don't know, 0.1, or it can go from 0 all the way to 2, right? So anywhere in this range is fine. So we can say that x is valid, right? Let x range from anywhere from 0 to 2 meters, right? So 0 meters to 2 meters. And we can draw this little section, right? We can say that it kind of looks like so, right? And we can analyze the forces that act on this section, right? And this is a section AA. You see it right here, AA. And the whole goal of this is I want to find the shear force, right? VAA. And I want to find the moment AA, or just A, right? I'll just call it minuscule a, right? So that's the whole point of this, right? Okay. And this is because nothing changes from A to B in this case, right before B, not when this 19 kilonewton force is acting, right? And then nothing changes from B to C, and then nothing really changes from C to D, right? But we'll get to that. Okay. So on this section, I want to find, as I said, I know that when I split this section open, anywhere between A and B, I'm going to have a shear force and I'm going to have a moment, right? So let's draw those. So I'm going to have a shear force. I'll call this V small a, and a moment, M small a, right? This represents my distance x. Remember, it can be anywhere from 0 to 2, right? And this is 0, right? So it goes from 0 all the way to this section AA. And x can be, in this case, 0 all the way to 2. Hopefully that's understood. I've said it like a few times now. And what else am I missing? Well, I'm missing my forces that I have right here, right? My shear force and my moment. What did I say they were? I said that VA is negative 13 kilonewtons, so therefore it actually acts downwards. So I'll call this V capital A. So V capital A is negative 13, or 13, right? So 13 kilonewtons. And then my moment acts clockwise and it has a value of 8 kilonewtons. So I'll draw that as well. So 8 kilonewtons. 8 kilonewtons. Kilonewton meters. Right? Okay. What I'm going to do now is I want to find VA and I want to find MA. Right? How do I do that? Well, VA is fairly simple. I can just take a sum of forces in the y direction, right? And I want you to not understand, I want you to be certain that for the diagram we have here, there are no other forces that are acting, right? That has to like go through your mind, right? You have to understand there are no other forces acting on like this section that we're taking, right? So that has to be crystal clear. So if we take a sum of forces in the y direction and we set this is equal to 0, we're going to end up getting that V capital A is equal to, in this case, negative VA, right? And then therefore, V small a which is what I'm looking for. I'm sorry this is confusing, but once we get to B and C, it'll go away. Or actually, let me just rewrite this because we don't have VA. So basically, if I take sum of forces in the x direction, I have negative 13 kilonewtons, or the y direction, minus VA. I'm going to end up getting that VA is equal to negative 13 kilonewtons, right? This basically just means that I misinterpreted the direction. It's actually upwards, right? But there, now I found a function that's valid from 0 to 2, right? Even though it's a constant function, it's still a function, right? With respect to x that represents my shear force, my internal shear force from A all the way to B, right? Hopefully that's understood. So I can call this, I can box this out. This is one of my functions, right? Right? So as AA, this section moves like back and forth, as long as it's between this range, my shear force will be this constant value, right? Beautiful stuff. Now I'm going to do the exact same thing, but for my moment, right? But my moments are going to be a bit different, and you'll see. If I take a sum of moments about my section AA, right? So about AA, I set it equal to 0. What's going to cause a moment? Well, I have this force, or I have this I've assumed it to be positive, right? So I'm going to say MA, right? I have this negative moment, this clockwise moment, which is going to be minus 8 kilonewton meters. I need to change the color. Right? And then what else will cause a moment about A? I have this guy, right? MA. I have this guy, 8 kilonewton meters. I'm missing one more. Well, I'm missing this lovely guy. This guy will also cause a counterclockwise moment, right? But the question is, remember, a moment is a force multiplied by distance, right? So it's going to cause a counterclockwise, so positive 13 kilonewton. What's the distance away? That's an important question. What's the distance from AA to the 13 kilonewton force? That's going to cause this 13 kilonewton force, and then it's going to like spin. It's going to cause a moment about AA. What's the distance? Well, my distance is simply x, right? Remember we said this distance from my relative, my 0, all the way to my section AA is x. Well, that's my distance, right? So I can just write multiplied by distance x. So as AA moves, this value will also alter, right? So now I can just isolate for my moment. MA is equal to, once I isolate, I'm going to get this function for my moment at my section AA. It's going to be negative 13 kilonewtons. I'm just going to keep it without the units for now. Multiplied by x. And I'm also going to keep the other one without units, right? But it's going to be plus 8. Right? So this represents, again, similar, it's not constant anymore, right? This represents a function for my moment, my internal bending moment within this range, within from 0 to 2 meters, right? So hopefully that makes sense. So these two functions, again, are only valid from 0 to 2 meters. And just like that, I'm done, right? Later on, I'll gather all my equations, and then I'll plot these guys, right? But for now, I found a valid function for my shear force and my bending moment with respect to x for this range, 0 to 2 meters. Now let me move on, right? Because something changes now, right? So I have to find a new function from B to C, or from 2 meters to 4 meters, right? So we can continue with that once I make this a bit smaller. Okay, we can move on. We can say now we're going to let X be valid, or let X range from 2 to 4 meters, right? 2 meters to 4 meters. And we're going to, amazing. We're going to draw the exact same thing, right? But now we're going to draw a section BB that ranges from 2 meters to 4 meters relative to this side, right? So X is like that. Okay. Let's see, this guy looks like that. Okay, this is my section BB. This is X, right, my distance. And then I'm going to draw this like this, right? From here to here is 2 meters. Now, the question is, from 2 meters onwards, is this one also going to be 2 meters? Well, no, not exactly, because this section BB, it can range. It can range from 2 meters, which is right here, to maybe, I don't know, maybe 4 meters is over here, right? So it can range from anywhere between these two values, right? So this isn't 2 meters anymore, right? From what we had up here, it's actually X minus 2 meters, right? For example, and I'll just write it first. So this is X minus 2, this distance right here. And if that doesn't make sense, for example, let's say my X is at 5. My X is 5, right? 5 meters away. Therefore, this distance right here would therefore just be 5 minus 2, or that's wrong. Let me gather my thoughts. Wait up. Oh, it can't be 5. Never mind, because arranging from 2 to 4, I'm I'm a bit tired. Yeah. Okay. Let's say this is 3, and then therefore this distance would be X minus 2, right? So 3 minus 2. Therefore, this distance is 1, right? And again, it can't be 5 because, like, 5 would be over here, right? But we're only speaking about this distance right here. Okay. Beautiful stuff. Okay. So, we can draw the forces once again, our external forces on the side due to the beam. So we can say that this is 8 kilonewtons, kilonewton meters. This is 13 kilonewtons, right? This force right here, as we said, acts at 2 meters, right? So it's 19 kilonewtons. 19 kilonewtons, right? And then what's going to happen at my section B? The whole point of this is I want to find the shear force and the bending moment, right, at my section B. So I can call this VB, and I can call this MB, right? Okay, I think that's everything. And what do we do now? The exact same thing we did last time, right? We're literally just going to take the sum of forces in the Y and sum of forces in the X, find a function for our bending moment and our shear force. So if we come over here, we say set Y to be positive, or sum of forces in Y, and positive is up, right? We're going to have negative 13. I'm going to drop the units from now on because it's going to get a bit cluttered. Plus 19. So negative 13 plus 19 minus VB, right? So therefore, and this is equal to 0, if I do my summations properly and I isolate for VB, I'm going to get my function for my shear force is going to equal 6 kilonewtons. 6 kilonewtons. So that's my function. Again, it's constant for my shear force at this section BB, valid from a range of X of 2 to 4. Do the exact same thing for my moment. Come over here. Sum of moments about section BB, 0. What forces are going to cause a moment? Well, let's include the actual moments first, right? So I'm going to have MB is going to cause a positive moment. I assumed it to be positive. Let's move this over. Right? I'm going to have a negative moment caused by 8 kilonewton meters on this side. And then this force and this force will also cause a moment, right? What is the distance away for this force? Well, it's simply x minus 2. What is the distance away for this force? Well, it's simply 2 plus x minus 2, which ends up being x, right? So this one is going to cause a clockwise moment, so negative, so 19 multiplied, sorry, I'm dropping the units, minus x minus 2, multiplied by x minus 2, and then the 13 is going to do a positive moment, 13 times x. If I isolate for my moment at my internal bending moment at my section BB, I'm going to end up getting my function to be MB is equal to 6x minus 30, right? So this is a function for my bending moment at my section BB, again, valid from a range of x of 2 meters to 4 meters. I'm going to box it off. I'm going to move on to my last and final section. Beautiful stuff. We're sailing smoothly. So we're going to do the last and final section, and this is section 4 meters to 6 meters, right? Okay, let me just organize this a bit. Okay. We're going to say let x range from 4 meters to 6 meters, right? I'm going to draw the exact same section once again, and this time for section CC. Let's include this in frame a bit. This is my section CC, right? I'm going to say that this distance right here is where point B is, and then, sorry, this distance right here. Okay, so this is 2 meters, right? This is 2 meters. Sorry, I have to keep this in frame as well. This is 2 meters, this is 2 meters, and then this distance, similar to last time, instead now is, this is going to be x minus 4, right? This distance right here, right? And this is because, as we said, if x comes out from here, right? And for example, now I can actually use 5 because my my range for x is 4 to 6, right? So if this is 5 meters, right? I'm going to say x minus 4, and y is 4 because this distance right here is 4, right? So x minus 4, 5 minus 4. Therefore, again, this distance right here would be 1 meter, right? So again, it's the exact same concept we did before with x minus 2, right? So this CC can range anywhere from, if this is 4, all the way, for example, if this is 6, right? So anywhere between that range. Wonderful stuff. Okay, I can start putting on my forces and my moments. Again, we have the 13 kilonewton shear force acting right here. We have the clockwise 8 kilonewton meter force acting like so. We have the 19 kilonewton force acting over here. And then we have a distributed load. Please, please, please do not put this 6 kilonewton force. Remember, this is a representation of this distributed load when your distance is 2 meters, right? Your distance is not 2 meters anymore. It could be 2 meters, right? If x is 6, right? If it goes all the way to 6, then yeah, sure, it's 2 meters. But that's not the case, right? So basically the same kind of idea where we have this distributed load, like so, it's 3 kilonewtons per meter, right? Okay, the same way that up here we multiplied it, 3 kilonewtons per meter, we multiplied it by the distance, 2 meters, to get one force that represents the entire distributed load of 6 kilonewtons, right? That acts at the center of the distributed load. The same exact concept, right? We're going to multiply our distributed load value by our distance, which in this case is x minus 4, right? And where does it act? The same way that, for example, this distance, it acts 1 meter away, right? And this entire distance is 2 meters, right? It acts halfway point, at the halfway point. Here, it's also going to act at the halfway point. And don't overcomplicate things. It's just simply x minus 4 divided by 2, right? You don't need to simplify. Like, just keep it like that for now, right? Easiest way. You could simplify, but I don't know if you like you like life at its hardest, right? Okay. So that's what we're going to do. We're going to say that this distributed load can be summarized as a single force, not of 6 kilonewtons in magnitude, but instead of 3 kilonewtons multiplied by x minus 4, right? A force multiplied by distance, right? Okay, and where this acts, again, it acts at this distance, x minus 4 divided by 2, right? Beautiful stuff. So this accounts for even if my CC section moves around, this will automatically adjust, right? It's a function, right? Beautiful stuff. Okay, I think that's oh, never mind. We have to add our actual, the things we want to find, right? So the things we want to find are our shear force at our section C and our moment at our section C, right? And now I think that's all, as long as I add this guy right here, where this represents x, right? Okay, we can start taking our sums of forces and sums of moments. If I take the sum of forces, or sum of forces in the y direction, set it equals 0, I'm going to end up getting that I have the negative 13. I'm going to drop the units, negative 13 plus 19 minus 3x minus 4, right? Minus VC is equal to 0. I'm going to end up getting that, and it's interesting to be honest, because VC is no longer a constant, right? VC is now a function, right? Or constant is still a function, but like now it actually has the x variable within it, right? So it's linear, plus 18. So that is a function that is valid from x is equal to 4 to 6, or x can range from 4 to 6 for my shear force, right? Okay. Now I can do the exact same thing for my moment. So my moments about section CC. And I'm going to end up getting that I'll put down my typical moments first, right? So MC, say 0, start over here. 0 is equal to MC minus 8 kilonewton meters, right? This force will cause a moment, this force will cause a moment, this force will cause a moment, right? Let's go from left to right. This one has a distance of 2 plus 2, so 4, plus x minus 4, therefore it's just a distance of x, right? So it's simply 13 times x, right? This one, for the 19 kilonewton force, it's going to cause a negative moment about section CC. So it's going to be 2 plus x minus 4, therefore it's going to be x minus 2. So it's going to be minus 19 times x minus 2. And then lastly, this one is simply 3, my force. It's going to cause a positive moment. 3 x minus 4 multiplied by the distance. What is the distance? Well, the distance is simply x minus 4 divided by 2. Right? Amazing stuff. And it's going to cause a positive moment, a counterclockwise moment. Okay, I'm going to solve for MC, and what I'm going to end up getting is actually a quadratic function now. So I'm going to get the MC is equal to negative 1.5 x squared plus 18x minus 54. And beautiful. Just like that, after a lot of fun, I'm finally able to like plot my shear moment diagrams, right? Because now what I've done basically is I have functions that represent the shear force and bending moments for sections 0 to 2, from sections 2 to 4, and from sections 4 to 6, right? And these are them, namely. So all I need to do is plot them, right? So let's make this small once again. And I can plot them. Put this in that corner like so. Okay. Okay, so in effort to not make this video 2 hours long, we have summarized all this lovely stuff so we can plot our diagrams, right? Or we can plot our information. So pretty straightforward. This is a representation of the actual load, right? Pretend this is like the beam we have, and then these are the loadings that act on it. The exact same thing we did before. We have our reaction connections and then our two external loads, where this is a distributed load. So I won't waste too much time. We'll go ahead with actually plotting the shear force diagram and the bending moment diagram. For the shear force diagram, as we said, we start at our initial condition. What is our initial condition for our beam? Well, if we look at the beam, we start at negative 13 for our shear force, right? Okay, so let's put that on. So we start down here. So let's say negative 13 kilonewtons. So 13 kilonewtons. Perfect. I go to my first function defining my range of 0 to 2x, right? And that function is, and it agrees with our initial assumption, that from 0 to 2x, my function for my shear force with respect to x is a constant function of negative 13 kilonewtons. So as simple as that. So from 0 to 2, I'm going to have a function that is constant, negative 13. Okay, how about from 2 to 4? Well, I have a function that's constant of 6 kilonewtons, right, for my shear force. So as simple as that, I'm going to say that maybe 6 is about here, 6 kilonewtons. It's going to go up like this, straight up, and then it's going to travel from 0 to 4 linearly, or not linearly, constantly, to 6 kilonewtons. So this is from 0 to 2, and this is from 2 to 4, as per my functions. And finally, to round everything off, and one important thing about shear force and bending moment diagrams is that they always end up at 0, right? No matter what crazy stuff it does, it'll always end at 0. And so that's one thing to like know. If it doesn't end at 0, you know, you're in a pickle. Something's wrong. So you have to fix that. So that's a nice clue. What is our last range, or what is our last function for our shear force? Well, between 4 and 6, we now have a linear function. What does this kind of look like? Well, it's linear, right? But it doesn't look like this. It looks like this because it has a negative slope, right? A slope of negative 3, right? So kind of like that, right? So we can plot that, and we know it goes to 0, so we can do that. So it's going to go negative slope linearly to 0, and just like that, that is my shear force diagram, right? And just in case and the best thing with the equation method is, just in case if we want to check our answer, I can literally, since this equation is valid from 4 to 6, an x value of 4 to 6, I can just plug in 6 here, right? And it should give me 0, right? Well, if you do that, negative 3 times 6 plus 18 is equal to 0, right? And that perfectly aligns with our diagram. And if you plug in 4 here, it'll give you 6. So, you know, it perfectly works out. So that is your shear force diagram. We can move on to the bending moment diagram. The bending moment diagram, the initial condition, it's kind of counterintuitive because we always say that counterclockwise is positive. But there's this guy on YouTube, amazing for mechanics and materials. His name is Jeff Hansen, right? He always has this like kind of analogy that the clocks are in the kitchen, the clocks are above the counter. So in this case, when you're drawing bending moment diagrams, and even like torque diagrams for that matter, you have to make clockwise positive, right? So our initial condition is 8 kilonewton meters clockwise. So therefore, the clocks are above the counter. So it's going to be above, right? So we're going to start, actually, let's put it red. We're going to start with 8. 8 kilonewton meters. Okay, we're going to look at our first function. What is our first function? Well, it's negative 13x plus 8, right? So this is a negative function, or a not a negative. Oh, it's a linear function with a negative slope, right? How do I know where it goes? Does it like go like this? Does it go like this? Does it go like? Am I going to actually plot this out? Well, you have a function, right? So you can plug in a value. So you can plug in 2 into this equation, right? So if you plug in 2, so negative 13 times 2 plus 8, you'll get negative 18, right? So that is going to be our next point. So negative 18 might be around here, maybe a bit lower. Negative 18 kilonewton meters. How is it going to travel there? Well, it's going to travel linearly with a negative slope. So linearly with a negative slope. So therefore, between 0 and 2, our bending moment has this area. Okay, how about between 2 and 4? Well, 2 and 4, I can take my function. I have a positive slope, right? Then that is linear. So if I plug in 4 into this equation, I'm going to end up getting negative 6, right? 6 times 4 minus 30 is equal to negative 6, okay? Let's just put that here. Negative 6 kilonewton meters. It's going to travel linearly with a positive slope. And lastly, now this is a bit different. I have a quadratic. It's not different, but like you have a quadratic function, right? And I know that it has to end at 0. And if I plug in 6 into this equation, I know that it will end at 0. It will end at 0, right? The question is, and it's going to travel there in a quadratic fashion like this. But the question is, will it travel like this, how I have on screen right now, or will it travel like this, right? Concave up or concave down? That's like, if you don't see that properly, like this, or like kind of like this. Okay, that might be a bit confusing, but like, will it travel like this, right? Will it get more steep, or will it start off steep and then get more like exponentially or logarithmically, right? So that's the question. How do I know that? Well, with graphical method, it's a bit easier. There's this trick, but with equation method, to be honest, the only thing that comes to mind is you could plug in values and see which one, like you basically take the limit, which is a repetitive process. But like if you actually want to do it properly, that's how I would do it, like if I had to do it. But an easy way, and this is sneak peek of graphical method, is I look at the same section on my shear force diagram and I see, is it big and then small, or is it something like this? Is it small and then big, right? What does that mean? Well, if it's small and then big, my speed. Sorry. So basically, if it's small and then big, right, your speed is also going to be like that, right? So basically, what I mean by speed, I mean like slope, right? Your slope is also going to be small. If I take a tangent line here, it's basically 0, right? The slope. And then it's going to get big, right? It's going to start small and then it's going to travel fast, right? Like exponentially, basically. But if it's, in this case, big and then small, that's going to be the exact same thing. I'm going to have a large slope and then it's going to get small, right? It's going to have a large slope and then it's going to even out, like a logarithmic function, right? So if it looks like this, it's going to be logarithmic for the most part, or I think for all parts, right? And then if it's like this, it's going to be exponential, right? So hopefully that makes sense. And I think because the issue is, okay, what happens if it's like this? That it's the exact same concept. If it's big and then small, it's going to be big. Your slope is going to be big and then it's going to be small, right? And then if it's, how would the other one look like? If it's small and then big, and remember this wouldn't happen because it has to end at 0, right? In this case, it wouldn't end at 0. It wouldn't end here. That's wrong. But just as an example, it would be small and then big. Therefore, it would be, your slope would also be small and then travel fast, big. Okay, hopefully that makes sense. And that is better than doing your little limit calculations with this to find whether it's like this or this, because at the end of the day, this is different than this, right? Because there's different areas, right? If you take the integral or even the derivative, right? Okay, so let's plot it. So moral of the story, you should tell me by now whether this one should be logarithmic or exponential. I'll break it to you. It is logarithmic, right? So bigger than small. We have a strong slope and then it gets weaker. Okay, and just like that, your function goes to 0. You are done the bending or the shear force and bending diagrams. This is equation method. It is not fun. The only thing that's not fun, right? But yeah, the graphical method is much, much simpler. I don't know how long this is right now, but like the graphical method will explain like 5 minutes, right? Basically, the graphical method says that if you're going this way, if you have the graphs in this orientation, you have your graph with your load with respect to x, your shear force with respect to x, and your moment with respect to x. If you're doing it like this, if you have it in this specific orientation, to get from here to here, you integrate. To get from here to here, you derive. As simple as that. That is the main concept, right? Okay, how do we do that? Okay, let's say we start off with this one, as you always are. Let's say we want to go down and then go down. Let's start with the shear force diagram. If I start at my initial conditions don't change. I look at my graph, I have a negative 13. Perfect, I start at negative 13 kilonewtons. Right. From 0 to 2, just looking at my diagram right here, do I have any function for my force? And by function, I mean, is anything changing? Well, no. So therefore, my function with respect to x for this range of 0 to 2 is equal to a constant of 0. Right. So if from 0 to 2, my function or my load function with respect to x is equal to 0, what did we say? We say when we're going from like this way, we integrate, right? We integrate, right? So what's the integral of this? If I take the integral of 0 with respect to dx, I just get a constant, right? So what's this constant going to look like? It's literally just a straight line. So therefore, on my shear moment diagram, from negative 13, from my initial condition, I'm just going to have a straight line until 2. Beautiful stuff. Okay, I look back at my diagram. Okay, what happens at 2? Well, at 2, I go up by 19 kilonewtons, right? So on my shear force diagram, guess what I'm going to do? I'm going to go up by 19 kilonewtons, right? And if I add 13 or negative 13 plus 19, I'm going to get 6. Perfectly aligning me at 6 kilonewtons, right? Okay, so we're going. Again, from 2 to 4, do I have any function that represents my load? Well, yeah, I do. It's simply just a constant of 0, right? Nothing's changing, right? If I take an integral with respect to dx of this, I'm going to get a constant function, right? I'm going to get the plus c, right? So therefore, again, nothing changes on my shear force diagram. To 4. Okay, let me redraw it. Like that, like that, like that, like that. Okay. Now I get to 3, right? I get to 4. Okay, something is changing or something is happening now between 4 and 6. What's happening? Well, my load function is a constant now, not of 0, but of negative 3, right? It's going down throughout this by negative 3 kilonewtons per meter, right? You can say that this is like a linear line, right? Or not a linear line, but like a constant, right? Okay, let's take an integral of this function. Well, what am I going to get? If I take an integral of negative 3 dx, I'm going to get negative 3x plus c, right? Well, look at my beautiful function for my shear force, which we did in equation method. Does that not look familiar other than the plus c? It is a linear line with a slope of negative 3 that leads to 0, right? How beautiful is that? It perfectly works out. So I'm going with a negative line or a negatively sloped linear line to 0, right? How do I know it ends at 0? That's one of the downsides of graphical method. You can't check your work exactly. Where equation method, I could just plug in 6 and figure it out. But with graphical method, there isn't, to my knowledge, like a specific way to check your work other than checking if you did it properly. But yeah, see, we take an integral of this linear function, which has a value of -3, right? Because it's going down. And then we get -3x, and it beautifully works out. This is a line with a slope of -3, right? That's linear. Beautiful stuff. And just like that, we've gotten to our lovely shear force diagram within a matter, because it took me to explain it a bit, but you know, if you were actually doing this, it wouldn't take you long. Similarly, with the bending moment diagram, again, from here, unless you want to take a double integral and just jump ahead, but you can just go like this, right? Okay, I start at my initial condition, which is a positive 8 clockwise kilonewton meter, what do you call it, moment, right? I start at positive. What goes on next? Well, I'm going to take an integral of from -3, -13, from 0 to 2 on my shear force diagram. I have a function of -13, right? And this is valid for 0 to 2. If I take an integral of this, I'm going to get the integral of -13 dx is equal to -13 x plus c. Look at my function. How beautiful is it? Like, it's actually wonderful. Like, look how, like, it just perfectly works together, right? So I'm going to have a negative line, right? A negative line, negatively sloped linear line, all the way to -18, right? How exactly do I know it's -18? Well, I can just take the area. What is the integral? It's just the area under the curve, right? So if I take the area of this block, it'll give me how much to go under by, right? Because -13, and look how beautifully this works out. -13 is my height, 2 is my width. -13 times 2 is equal to -26. I start at 8. What is 8 minus 26? Well, you got it. It is -18. It is spectacular how this stuff works out. And again, how do I know how to get there? Well, I just took the integral of this constant function. I go down with a slope of -13x. Beautiful stuff. Okay, I got this far. What's next? The exact same thing, right? If I want to find where my next step is going to be, I'm going to take the area under the curve from 4 or from 2 to 4. 6 multiplied by 2, which gives me 12. So I'm going to go -18 plus 12, which is equal to -6, which is exactly my point, right? And then how am I going to get there? Well, a positive linear slope of 6x. Just the integral, right? Beautiful stuff. It's linear. Okay, last but not least, I want to go to 0. Let's just clear this a bit. So to do that, it's the exact same thing we've been doing before. This looks to me like a negatively sloped linear line, right? So maybe negative, I don't know, a constant multiplied by x. Let's just say -x, right? If I take the integral of -x dx, I'm going to get maybe -x squared over 2. These don't, like, over 2 doesn't really matter to me. But what this tells me is I'm going to have a quadratic, which perfectly aligns, again, with my beautiful formula, right? So I'm going to have a quadratic, as we said, a big and then small, right? So a big slope and then a small slope, right? So it's going to come up like this to 0. And there is one thing that comes to mind, actually. How do we know it? I think I said before that I couldn't think of a way to, like, actually know how it comes to 0. In graphical method, it came to mind. So basically how we know is like what we did before. We take the area under the curve. So for this triangle, right here, it's just 1/2 base times height. What is the base? Well, it's 2 meters. What is the height? Well, it's 6 meters, right? So if I do 1/2, 2 times 6, right? And this is positive, right? I'm gonna get 6, right? So I start with -6, and then I'm going to end with -6 plus 6, which gives me 0, right? So I beautifully end at 0. And then if I wanted to look back at this example, if I were to take the area of this is like this is going down, right? So it's -3 as my height. I know it looks weird, but like arrows are going down, like it's acting down. So -3 is my height. This is 2, right? So -3 times 2 is equal to, not 0, -6. However, if I start at 6 here, plus -6, I'm going to end at 0, right? So absolutely beautiful. Basically, long story short of graphical method, two things. You go like this, you integrate. Go like this, you derive. And how basically you actually integrate? Well, number one, you're going to see the value of how much you're going to go down by, right? If there's nothing acting, then you don't need to worry. It's simply constant. If there is something that does act, then you might have to take like an area, right? To see what specific number you need to go down to or go up to, right? And then you also need to realize how to get there. I think this is the best example that describes this process, right? So number one, I'm going to, if I start at 8, I want to see how much I'm going to go down by. So I'm going to go down by -13 multiplied by this distance is 2, right? So multiplied by 2 is equal to -26. So this is how much I'm going to go down by, which brings me at -18, right? How am I going to get there? Well, how am I going to get there is simply just the integral of this line. And if this line is -13, the integral of that would be -13x. I don't really care about the 13 in this case. I just care how it gets there, right? It's a negatively sloped linear line, right? And just like that, that is the graphical method, right? As soon as you do like a bit of examples, you'll probably get it if you didn't get it through this explanation. But yeah, it beautifully all works out. And even if you want to see something, if you take a derivative of this, or no, not of this. If you take a derivative of this function, for example, -1.5 x squared, just to prove that the derivative part also works, because we didn't address that, right? If I take a derivative of this function with respect to x, what am I going to get? Well, the -54 is going to go to 0, right? The -54 is going to go to 0. This one is going to become a +18. This one is going to be -1.5, so n minus 1, so 2x to the power of 1. So this just becomes -3x. If I bring this down, -3x, right? And guess what? That is my shear force equation between 4 and 6, right? And then if I take the integral, I'll get the same thing. So hopefully that was helpful. That is shear and bending moment diagrams. We're going to buzz through them from now on. So hopefully that explanation was good enough, yeah?